Hello! In this video we're going to cover some ideas in combinatorics. In particular, the learning outcome for this video is for you to be able to derive expressions for the number of arrangements of a set of indistinguishable objects and the number of arrangements of a set of distinguishable objects. You should already have covered this material in PMA 1020 in a more mathematically rigorous way. Furthermore, we have already encountered some of it when we studied the binomial random variable and the binomial coefficient that appears in the probability mass function for this variable as shown here. It is nevertheless worth working through this material again, as my experience has been that students find this material rather difficult. During the week, we will thus spend some time on problems that will hopefully help to reinforce these ideas. To get us started on revising this material, let's review the material on the binomial coefficient that was covered in the video on the binomial random variable. In that video, I explained that we need the binomial coefficient because there are multiple ways of arranging the k-successes amongst n trials. For example, if I do 2 trials, there are 2 ways of ordering the successes and failures if we want the probability of having exactly one success. The success could have come on the first trial or on the second trial. The binomial coefficient thus comes from considering the mathematics of counting the number of arrangements of things, or as it is otherwise known, the field of combinatorics. In these last few slides, I will thus explain the aspects of combinatorics that we need to understand in order to use combinatorics within probability theory. Before considering the business of the binomial coefficient, let's consider a simpler question. How many ways are there of arranging n distinguishable objects? In other words, how many different looking ways can we arrange n objects if we can tell apart all of the n objects? To explain this, I will use coloured circles like the blue one shown here. If I have only one circle, there is clearly only one arrangement. The moment I introduce a second red circle, however, I find that there are now 2 arrangements, namely red-blue and blue-red. Furthermore, on introduction of a third green circle, I find that there are 3 places that I can place the green circle in the blue-red pattern shown here. That is to say, I can introduce the green circle before the blue and red circles, after the blue and red circles, and between the blue and red circles. Furthermore, if I remember that there are 2 ways of arranging the red and blue circles, I find that there are 6 arrangements of the 3 balls in total, namely red-green-blue, red-blue-green, blue-red-green, blue-green-red, green-red-blue, and green-blue-red. There is a simple pattern here. In general, if we have n distinguishable objects, there are n factorial ways of arranging them. To convince yourself of this, pause the video and enumerate all the ways of arranging 4 distinguishable objects. We are now in a position to answer our original question on how to arrange the k successes and the n minus k failures amongst the n Bernoulli trials that we have performed in generating our binomial random variable. To do this, we need to suppose that we have only 2 types of objects, successes and failures, or, in the pictorial example shown here, red and blue circles. Normally, we cannot distinguish between any pair of red circles or any pair of blue circles. Let's suppose for a moment that we made all the objects distinguishable by giving them numerical labels as shown here. We now know from the rule that we have just learned that there are 6 factorial ways of arranging these objects. The problem, however, is that in actuality we cannot distinguish between the red circles. If we swap these 2 red circles, the sequence appears not to have changed. Help is at hand, however, as we can use the rule that we have learned to calculate the number of identical ways there are of arranging the 4 red circles in this sequence using the rule that we have just learned. Furthermore, we can also count the number of identical ways there are of arranging the 2 blue balls in this sequence. In particular, there are 2 factorial identical ways of arranging the 2 blue circles in any given sequence, and 4 factorial ways of arranging the 4 red circles in any given sequence. In other words, there are 2 factorial times 4 factorial ways of arranging the individual blue and red circles in every distinguishable arrangement of blue and red circles. The number of distinguishable arrangements of blue and red circles can thus be found by taking the 6 factorial ways that there would be of arranging the circles if they were all distinguishable, and dividing this by 4 factorial times 2 factorial to reflect the fact that each distinct arrangement of circles can be constructed in this number of different ways. This is how the binomial coefficient is defined, and it is how we can calculate the number of ways of arranging the k successes and the n minus k failures in our binomial random variable. Let's finish by summarizing the 3 important results of combinatorics that we will need to use for all the problems that we are going to cover this week. The first of these results is that if we have n distinguishable objects, like these 4 differently colored balls, then there are exactly n arrangements that they can have. In contrast, if we have n distinguishable objects and m indistinguishable objects, for example, if we have a blue and a green circle that can be distinguished and 2 red circles that cannot be distinguished, then there are exactly n plus m factorial divided by m factorial arrangements that we can place these objects in. Lastly, if we have n objects of type 1 and m objects of type 2, for instance, if we have a mixture of n green and m red circles, as shown here, then there are exactly m plus n factorial over m factorial times n factorial ways of arranging these objects. These 3 results appear again and again in statistics and in other branches of mathematics. It is thus well worth spending the time to memorize them and to learn how these results are derived. They are all very important. Thank you for your attention.